Hello everyone and good day. So we are the Group 3 presentator and we are here to report about a certain topic that need to be discussed later. So before anything else, these are the Group 3 members. So these are the remaining topics that needed to be tackled later on. So the first one is the solution of ordinary differential equations, the initial value problems. And the second one is the Euler's explicit method, modified Euler's method, and midpoint method. And the third one is Runge-Kutta methods using the second, third, and fourth methods. And the fourth one is modified Euler's predictor and correctors method. So we're gonna discuss the solution of ordinary differential equations of initial value problems. So numerical methods for solving ordinary differential equations are the methods that integrating the system of first order differential equations. Well, since a higher order of differential equation can be reduced of having to a set of ordinary differential equations. So let's have a first quick review of differential equation. So differential equation is an equation taking a form of dy over dx is equals to the function of x. So it is an equation with a function and one or more of its derivatives. We all know that differential equations are more important topic in calculus, of course, engineering and sciences. A lot of the questions that we work with in sciences and engineering are derived from a specific type of differential equation called an initial value problem. So the solution of an ordinary differential equations or ODE. So it is a solution of a differential equation is a function or a relation that satisfies the equation. So these are types of solutions that we need to be tackled, the general solution and the particular solution. So general solution is a set of all solutions of a differential equation. It is a complete solution. It contains one or more arbitrary constants called parameters and order differential equation as n parameters. While particular solution is a solution which free of arbitrary constants and also satisfies a unique conditions. So the initial value problem. The problem of finding a function y of x when we know its derivative and its value y sub 0 at a particular point x sub 0 is called an initial value problem. This problem can be solved in two steps. The first one is solving the general solution as you see the first figure, and the second one is using the initial data by plugging it into the general solution and solve for c. So this is the example. Solve for initial value problems. So this is the given equation. Dy over dx is equals to 10 minus x. And value problem is y0 is equals to negative 1. So again, using the step 1, we must have the come out of general solution. So dy over dx is equals to 10 minus x. So dy is equals to 10 minus x dx. So using the differential, so the differential of dy is equals to the differential of 10 minus x dx. We have the final outcome of y is equals to 10x minus x squared over 2 plus c. So the step 2, we input the given initial values, which is x is equals to 0 and y is equals to negative 1. So putting that and substitute, negative 1 is equals to 10 times 0 minus 0 over 2 plus c. So we have the come out of c is equals to negative 1. So the value of c, we must input it to the general equation. So y is equals to 10 minus x squared over 2 minus 1.
Good day everyone. So we are now going to discuss about Euler's explicit method. And by the way, I am Joyce Mingito. Euler's explicit method. It is a computational method to approximate the general or particular solution of first-order differential equations. So instead of directly solving the particular required values by using different direct methods of computation, an approximate may be enough as long as the values are close to the real ones. For example, we have here a graph of a differential equation. Euler's approximation method has the ability to identify points that are close to the exact values. Although there could be some difference with the result, but using closer step size may make the value more accurate. Right now, we are going to get the formula of this method. So we have here a hidden differential equation curve. We also have here an initial points given with coordinates of x sub 0 and y sub 0. To proceed with the next points with coordinates x sub 1 and y sub 1, we can see here that x sub 1 was completed by adding the step size that was from the previous x, which was the x sub 0. And the value of y sub 1 is a little complicated because the distance between y sub 0 and y sub 1 is undefined. So we are going to use a slope that is actually a derivative of y with respect to x, which is the dy over dx. And take note that slope is also equals to rise over run. Since dy over dx is a differential equation, we can equate rise over run as y over h. So the formula of y is equals to h multiplied by the differential equation. For the next point, it is still following the same procedure. We just have to change x sub 0 to x sub 1. On the other hand, for y sub 2, we just have to change the y sub 0 to y sub 1 plus h times the functions of x sub 1 and y sub 1. So we just have to continue the same process until the required x. So if we're going to solve for the next point, we just have to use x sub n minus 1 plus h. For example, we are going to get the fourth iteration. The value of our n will be 3, and 3 minus 1 is equals 2. So the formula of our x will be x sub 2 plus h, and so with the formula of y. So that is now the formula of Euler's explicit method. We are now going to proceed with a sample problem so that we can showcase this method. Approximate y if x is equals to 0.60 using Euler's method with the equation by using a step size of 0.15. Initial x and y are 0. The differential equation is y prime equals to x plus 3y. So the givens are x sub 0 is equals to 0, y sub 0 is equals to 0, h is equals to 0.15. And we're going to find the value of y if x is equals to 0.60. So let us solve first the values of x by using the formula x plus h. Starting with x sub 0 is equals to 0, x sub 1 is 0 plus 0.15 is equals to 0.15. X sub 2 is 0.15 plus 0.15 is equals to 0.30. X sub 3 is 0.30 plus 0.15 is equals to 0.45. And x sub 4 is 0.45 plus 0.15 is equals to 0.60. And now that we have found out that 0.60 is the fourth value of x, we are going to stop there and proceed with the values of y. So the formula will be y plus h multiplied by the functions of x sub n minus 1 and y sub n minus 1. So we start with y sub 0 equals to 0. Next, we have y sub 1 is equals to y sub 0 plus h times x plus 3y. So we're just going to substitute the values of h and x. And by that, y sub 1 is equals to 0. For y sub 2, we're going to substitute the values of y sub 1, the h, and also the x. And by that, y sub 2 is equals to 0.0225. For y sub 3, we're going to do the same substitution. So y sub 3 is equals to 0.077625. We're going to do the same substitution of values with y sub 4, and by that, we have y sub 4 is equals to 0.180056. Finally, we have found out that y, if x is equals to 0.60, is equals to 0.180056, and that is our final answer. And that ends my discussion about Euler's explicit method. Thank you for watching. Stay safe.
Hi everyone, I am Karin Love and right now I'll be discussing about the modified Euler's method. So modified Euler's method is also called as Yoon's method or Euler predictor corrector method. So in this kind of method, this tries to reduce the error by taking the average of the two tangents. In the previous discussion about the Euler's method, it is a tangent line from the first point is used to determine the second point, wherein there's some discrepancy while using that method. There's a error. So this is the graph, as you can see. Here in the graph, this red dot, this is the first point of the curve, and we have this first tangent from the first point, which is from the first point. In Euler's method, to determine the second point, we use the first tangent. So there, we have the second point. And so on. We have the second, from the second point, we got the second tangent, and then we come up with the third point. So that is the Euler's method. So there's an error. As you can see, here is the error. So here is the error. As you can see that. So in modified Euler's method, we tend to reduce the error by taking the average of two tangents. So this is the average. As you can see this line over here, the average of the two tangents, wherein it reduces the error. So as you can see, there's a very small error right there. As from the last topic about the Euler's method, this is the formula. X sub 1 is equals to x sub 0 plus h, and y sub 1 is equals to y sub 0 plus h times the function of x and y sub 0. In the modified Euler's method, we have the function of the two tangents. In the first tangent, we have the x and y sub 0, wherein y sub 0 prime is equals to dy over dx. It is the function of x and y sub 0. And in second tangent, that is x sub 1 and y sub 1. And so that is y sub 1 prime is equals to dy over dx and equals to function of x and y sub 1. If we come up with the average of this one, because again in modified Euler's method, we take the average of the two tangents, this first tangent and the second tangent. So we need to have the formula for the average of the two tangents. So here it is. Y sub m is equals to the summation of first tangent and second tangent, which is this is the first tangent and this is the second tangent. So summation of the two over 2, all over 2. That is not the final formula or equation. So from Euler's method, as again in the previous slide I have showed you, this is the Euler's method, the equation for the Euler's method. And we all know that is this one plus h, and this is the function of x sub 0 and y sub 0 is same as this one. So we have the value of y sub m, so we have to put it there. So we come up with this equation, y sub 1m is equals to y sub 0 plus h times the equation for ym, which is this one, again, this one. So we have this, put it here. So the equation for this modified Euler's method is y sub 1m is equals to y sub 0 plus h multiplied by the function of x and y sub 0 plus the function of x and y sub 1 all over 2. And again, from the Euler's method, this is called the predictor equation. And from this equation here, that is called the corrector. This is our example for this discussion. We have this example. Approximate y 0.20 using Yoon's method with the equation by using a step size of 0.10. Initial x and y are 0. Y prime is equals to x plus 3y. So this y prime, as we all know, that is dy over dx. So dy over dx is equals to x plus 3y. So right here, again, I have already given you this equation, predictor and the corrector equation. And we also have this x sub 0 plus h here. Okay, so this is used to identify the value of our x sub 0, our x sub 1, x sub 2, and so on. So first, we have, by the given, the initial x and y are 0. So we have here x sub 0, which is 0, and y sub 0 is equals to 0. Next, so through the use of this predictor equation, we have y sub 1 is equals to y sub 0 plus h times x plus 3y. So if we substitute this given here, we have the value of y sub 0, which is 0, so here, plus 0.10, which is the h, which is given here. The step size is 1.10. So that is the h. Multiply by, again, diba, in the equation, this is the function of x and y sub 0. But we already know, we have this given over here that x plus 3y. So we substitute that x plus 3y, and we have the x sub 0, which is 0, and then plus 3 times y, which is the value of y is 0 here. So times 0. So the answer is 0. So that is the answer, well, that is the y sub 1 of the predictor method. Here in the second, in the corrector, we have this formula again given in the previous slide, function of x and y sub 0. So again, it is given that x plus 3y. So here we have, and here. Y sub 1m is equals to 0 plus the value of h, which is 0.10. Multiply by the value of x sub 0, again, this one, so 0, plus 3 times y sub 0, which is 0, again here. Plus, okay, from the x and y sub 1. So we have the value of x sub 1, which is 0.10. So we input it here, plus 3 times y sub 1. So what is our y sub 1? It is 0 here, over 2. The answer, y sub 1m is equals to 0.005. Moving on, again, same process, repeat. The process is being repeated. So we have this x sub 2 is equals to 0.20. If you're asking why is the value of x sub 2 is equals to 0.20, that is because, again, here in the formula, x sub 0 plus h. So same here, we have x sub 0, which is given, we have 0. So our value of x sub 1 is equals to 0 plus 0.10. And in the value of our x sub 2, so that would be x sub 1 plus h, or 0.10 plus 0.10. I hope you get that. Let us proceed with the second y sub or the y sub 0 here in the predictor. Same with this equation, y sub 0 is equals to y sub 1, okay? Y sub 1, which is y sub 1m, which is this one, 0.005, plus h, which is 0.10, multiplied by 0.10, that is the value of our x sub 1, plus 3 times the value of our y sub 1, which is again this one. We will not be using the value of y sub 1 from the previous predictor method. So we shall use this corrector, the answer for the corrector. So y sub 2 is equals to 0.0165. Now let us proceed here in the corrector method. Y sub 2m is equals to y sub 1m plus h multiplied by x plus 3y sub 1m plus x plus 3y sub 2m. I mean sub 2 over 2. So again, we have the value of y sub 1m, which is 0.005, so right here, plus the value of our h, which is 0.10, multiplied by x. So what x? That is x sub 1, which is here. So 0.10 plus 3 times the value of our y sub 1m, which is 0.05, plus x sub 2, which is this one. So 0.20 plus 3 times the value of y sub 2 from the predictor method. So 0.165 over 2. So we get this y sub 2m is equals to 0.26025. So that is it, guys. That is how you use the modified Euler's method, and I hope you have learned something from my discussion, and let us proceed for another discussion to be done by my group mates. Thank you very much.
The next method is the midpoint method. It is also known as the second-order Runge-Kutta method or the improved polygon. It improves the Euler method by adding a midpoint in the step, which increases the accuracy by one order. It illustrates another simple modification of Euler's method to improve the estimate of the slope. The graph shows the depiction of the midpoint method, predicting the value of the midpoint of the interval, which is the slope, or the f of xi plus 1/2 and yi plus 1/2, in order to know the value of y when x is equals to a number. First is to predict a value of y at the midpoint of the interval using the formula yi plus 1/2 equals yi plus f of xi and yi times h over 2, where h is the step size. Then this predicted value is used to calculate the slope at the midpoint. We have y prime I plus 1/2 equals the slope. Then this slope is then used to extrapolate linearly from xi to xi plus 1/2 using the formula yi plus 1 equals yi plus the slope times h. For example, use midpoint method to solve this equation y prime equals x minus y over 2. For range x equals 0 to 0.1 and h is equals to 0.1, where y equals 1 when the value of x is equals to 0. Now we have the given xi equals 0, h equals 0.1, yi equals 1, and the unknown is the value of y when the x is equals to 0.1. The first is to predict a value of y at the midpoint of the interval using the formula yi plus 1 half equals yi plus f of xi and yi times h over 2. Now substitute 1 plus f of 0, 1 times 0.1 all over 2. To substitute the values of x and y back to the equation, we have 0 minus 1 over 2 equals negative 0.5. Now back to the formula, yi plus 1 half equals 1 plus negative 0.5 times 0.1 all over 2 equals 0.975. Then, this predicted value is used to calculate the slope at the midpoint. The 0.05 is the value of x at the midpoint of the interval, while the 0.975 is the predicted value of y at the midpoint of the interval. So substitute the values back to the equation. We have 0.05 minus 0.975 all over 2 equals negative 0.4625. This slope is then used to extrapolate linearly from xi to xi plus 1 half. The formula yi plus 1 equals yi plus the slope times h. Substitute 1 plus negative 0.4625 times 0.1 equals 0.95375. Therefore, the value of our y when x is equals to 0.1 is 0.95375.
Good day everyone, I am Jim Sondra. Today I will talk all about the second example of midpoint method. Use midpoint to solve this equation. This is already in the derivative form. So this is the slope. For range x equals to 0 to 2, and step size is 0.5 where y equals to 1. So symbol sa step size kay h. So x ni siya guys, kanang n, x ni siya. Sayop lang. So 0, 0.5, 1.0, 1.5, 2.0. So nganon 2.0 raw gotob kay ang range man sa x kay 0 to 2. The middle interval sa 0 ug 0.5 kay 0.25. X equals to 0, y equals to 1, h equals to 0.5. So, mao na siya ang initial condition. Kining arrow. So, yi plus 1 half equals yi plus f xi yi times h over 2. yi plus 1 half equals 1 plus f 0, 1 times 0.5 divided by 2. So, ang value sa yi kay 1. So, f0, 1 equals 1 times 0 raised to 2 minus 1.2 times 1 equals negative 1.2. So, mo na siya ang slope. So, kanina, gikuha na ko na siya nga ray. Akong i-distribute ang value nila. So, ang kaning negative 1.2, ako na siyang i-distribute sa kaning f01. So, yi plus 1 half equals 1 plus negative 1.2 times 0.5 over 2 equals 0.7. Next, yi plus 1 half equals f xi plus 1 half yi plus 1 half. So, mao na siya ang middle interval. 0.25 and 0.7. Ang 0.25, di rin siya gikan. Ang 0.7 sa kani. So, f 0.25, 0.7 equals 0.7 times 0.25 raised to 2 minus 1.2. 0.7 times 0.7 equals, ang answer kay negative 0.79625. Mao niyang midpoint slope. So, ang kaning answer, ato siyang gamiton nga ray. So, y plus 1 equals yi plus f plus negative 0.79625 times 0.5. So, nganong wala na siya over 2. Kaya ang h over 2 is to calculate the midpoint. So, answer is 0.601875. That's all. Thank you.
So good afternoon everyone. I am here to report the intro and background and overview of Rouge and Cota method. So 100 years ago, C. Rouge was completing his famous paper, The Work of View, in 1895, extended the approximation method of Euler to very elaborate scheme which was capable of greater accuracy. The idea of Euler was to propagate the solution to an initial problem forward by sequence of a small time steps. In each step, the rate change CF, the solution, is treated as constant is found in the formula for the derivative evaluated at the beginning of the first step. For the evaluation, x is equals to f of x, yx is equals to given a value of yxo. Yo, the first step is the initial of xo, which is slightly larger than the value of z. Say the approximation solution that is the point taken to be y in the forward of the solution. So the characteristics features Rouge of Kuta methods of the evaluating of the function f a number times in working the way through each step was established. These characteristics featured by Rouge and Kuta methods of evaluating the function if f a number of times in a working the way each step was established. Section 2. The early work Runge and his immediate successor Hyun and Kota, laying the foundations for these methods and developing practical methods of increasing accuracy and efficiency. Section 3. The conditions of Rojo and Kota method has given the order of accuracy, although we will concentrate on the conditions for the general autonomous system of equations. We will also compare this theory with that for the single first order equation. In section 4, the derivation of methods of increasing high order in the context of non-order barriers. This complication of relationship between attainable order and number stages for classical explicit methods is the sharp contrast to the simplicity of the corresponding questions for the more general implicit Rouge and Cotton methods introduced in the section 5. So now, in section 6, is devoted to stability the questions of Rouge and Cota methods. These questions range from step size limitations due to what is now called mild stiffness and identification of implicit, a stability of nonlinear generalization known as an algebraic stability. Section 7. The need of select of efficient step size sequence automatically local error. Estimation is necessary methods in achieving this, especially through computations performed within the same steps. So that's good, Bill. Thank you. So let us proceed to the next reporter.
I am Kimberly Nakwa, and we, I I will be reporting the Roncota method, and it is just an overview because my other members will be reporting the second, third, and fourth method. So the second order Roncota method. It is a numerical method for solving a standard differential equation of the type. So, only the first order differential equation can be solved by using the Ron-Cotta method. In other section, the Euler and Ron-Cotta methods are used to solve the higher order ordinary differential or coupled differential equation. So this is the example of the Ron-Cotta method. And the next one is the third order Ron-Cotta method. It is a numerical method for solving a standard differential And this method finds an approximate midpoint of the second line using the enhanced Euler method, then takes an average value of the slope at the left and the right ends and the midpoint. So this method uses the improved of Euler method to find an approximate method of the second line, and then takes weighted average of the slope of the left and the right endpoints and midpoints. And it is also same as Simpson's rule of numerical approximation of integrals from calculus 2, just as the Euler method and then improve Euler's method. This method can be easily put in a spreadsheet. So this is the example of the third method. So the last one is the fourth order Ron-Cotta method. So this method, with Euler's method and improve the Euler's method, we can repeat the process, and it is a popular technique for practical computation, not just for the educational purposes. And also the steps are well suited to programming into a computer. Just loop loop through the basic algorithm as many times as needed to get the values you are interested in. And the first part of a spreadsheet for the Archiform method applied in the next page. So, Monisha. So this method is so powerful enough that it was a popular technique for the practical computation, especially spreadsheets. Yeah. So that's all. Thank you.
Our next topic is Range-Kutta method, the second order method. Range-Kutta second order method is a numerical technique used to solve an ordinary differential equation in the form of dy over dx equals function of x and y. Here we have the formula for the second order method. Y sub g equals y sub 0 plus k, where k is equals to 1/2 times k1 plus k2, and k1 is equals to h times function of x and y, k2 is equals to h times function of x plus h, y plus k1. So here we have a sample problem for second order method. Using second order method, solve dy over dx equals x squared plus 2y. With its initial condition, y sub 0 equals 1, x sub 0 equals 1, and h equals 1. Find y at x equals 1. So, solution. First, atong kuhaon ang value sa k1. Kani siya. Using the formula for k1, k1 equals h times function of x and y. Substitute value sa y sub 0 and x sub 0, pati ang sa h. Atong makuha ang 1 times function of 1 and 1. Kaning 1 and 1 represents the x value and y value. I-substitute na to siya sa ODE, which is x squared plus 2y. Makuha na to ang 1 squared plus 2 times 1 equals 3 times 1. So ang value sa k1 kay 3. Na natin value sa k1. Next is k2. Using formula for k2, k2 equals h times function of x plus h and y plus k1. Makuha na to ang 1, substitute ang value sa h, 1. Next is x, value sa x kay 1, plus h, which is 1 sad, so 2. Then sa y na to, 1 sad ang value, plus k1, which is nakuha na to ganiha, muni ganiha, 3. So 4. So So the same ganiha, ato i-substitute sa ODE which is x squared plus 2y. Then makuha na to ang value sa k2 which is 12. So nanatay k1 and k2. Next is kuha na to ang k. So substitute sa formula nga k equals 1/2 times k1 plus k2. Makuha na to ang 1/2 times 3 plus 12 equals 7.5. Nanatay value sa k. So lastly, maggamit nito sa formula nga y equals y sub 0 plus k. Substitute ang value sa y sub 0 and k. 1 plus 7.5, makuha na to ang 8.5. So final answer is y equals 8.5 at x equals 1.
This is the third order Rouge-Kutta method. Another RK method is the RK3 method, which involves three values of k. The classical equation for RK3 is y sub n plus 1 equals y sub n plus h over 6 times k sub 1 plus 4k2 plus k3, where k sub 1 equals function of x sub n and y sub n. K sub 2 equals function of x sub n plus 1/2 h and y sub n plus 1/2 k sub 1 h. And the last is k sub 3 equals function of x sub n plus h and y sub n equals k sub 1 h plus 2 k sub 2 h. So guys, nani siya step by step solution for this method. Ang step 1 kay solve for k sub 1. Niya ang step 2 solve for k sub 2. Niya step 3 solve for k sub 3. Ang step 4 is solve for new pair x sub n plus 1 and y sub n plus 1, which is x sub n plus 1 equals to x sub n plus h, and y sub n plus 1 equals y sub n plus h over 6 times k sub 1 plus 4k sub 2 plus k sub 3. Ang last step guys kay repeat step 1 to 4 until the required value of x is reached. So let's go to the example guys. Consider the differential equation shown below. Y dy plus 2x dx equals e raised to the power of x dx. Solve for the value of y when x equals to 2. If 0 and 1 is part of the equation, use the classical RK3 method and h equals to 0.25. Note that from the analytical method that the true value is 2.403770. So guys, inani ang pag-solve sa RK3 method. For x sub 0 and y sub 0 equals to 0 and 1. Nanata sa first step. Unsa kitong first step? Ang first step kay solve for x sub 1. So let's start the solving the k sub 1. K sub 1 equals to function of x sub 0 and y sub 0 equals function of 0 and 1 equals e raised to the power of 0 minus 2 times 0 over 1. Nya, ang answer na kay equals to 1. Ang step 2 kay solve for k2. X sub 0 plus 1/2 times h equals 0 plus 1/2 times 0.25 equals to 0.125. Y sub 0 plus 1/2 times k sub 1 times h equals to 1 plus 1/2 times 1 times 0.25 equals to 1.125. K sub 2 equals to function of x sub 0 plus 1/2 times h and y sub 0 plus 1/2 times k sub 1 times h equals to function of 0.125 and 1.125 equals to e raised to the power of 0.125 minus 2 times 0.125 over 1.125. So, may equal siya 0.785021 ang answer. Step 3 kay solve for k sub 3. X sub 0 plus h equals to 0 plus 0.25 equals to 0.25. Ang y sub 0 minus k sub 1 h plus 2 times k sub 2 times h equals 1 minus 1 times 0.25 plus 2 times 0.785021 times 0.25 equals na siya kay 1.142511. K sub 3 equals a function of x sub 0 plus h and y sub 0 minus k sub 1 times h plus 2k sub 2 times h equals to function of 0.25 and 1.142511 equals to e raised to the power of 0.25 minus 2 times 0.25 over 1.142511. So, ang equal sana kay ang k sub 3 kay 0.686230. Nga ang step 4 kay solve for the new pair. X sub 1 equals x sub 0 plus h equals 0 plus 0.25 equals to 0.25. Ang y sub 1 equals y sub 0 plus h over 6 times k sub 1 plus 4k sub 2 plus k sub 3 equals to 1 plus 0.25 over 6 times 1 plus 4 times 0.78521 plus 0.68623 nga equals niya na kay 1.01496. So, this is the tabular presentation. Ang n kay 0, ang x sub n kay 0, ang y sub n kay 1, k sub 1 kay 1. Nga, k sub 2 is 0.785021 and k sub 3 is 0.68623. X sub n plus 1 is 0.25. N plus 1 is 1.01096. Since ang x kay wala man na reach ang value, since wala pa magyapon naabot ang x, mo proceed na sa tabalik, pero ako na skip kay taas-taas na itong discussion. Di ako ba mo report? Yeah, mga na ni ang final nga answer. Thank you.
Formula of fourth order Rukota method or RK4 is given below. So let the given differential equation b equals dy over dx equals fx and y initial condition of y equals y naught. When x is equals to x naught, then find the value of y equals y naught. Use Rukota method of fourth order. So find equals 0.2 for the equation of dx over dy equals to y minus x over y plus x. X naught, y naught, x naught is equals to 1, then taking h is equals to 0.3. So your f, x, and y is equals y minus x over y plus x. So x naught, initial value of y naught, x naught is equals to 1. So your y naught is equals to 1 and your h is 0.3. For your equation, y times x naught plus h is equals y naught plus 1 over 6 times k1 plus 2k2 plus 2k3 plus k4. For your k1, hf x naught plus y naught. So equals 0.3 times 0 plus 1 is equals to 0.3, 1 minus 0 over 1 plus 0 is equivalent to 0.3. For your K2, HF x naught plus h over 2 y naught plus K1 is equivalent to 2.
over 2. So your h is 0.3, f 0 plus 0.3 over 2, 1 plus 0.3 over 2. So equals 0.3 f 0.15, which is 1 plus 0.3 over 2, and your 1.1 is 0 plus 0.3 over 2. Is equals to 0.3, 1.15 minus 1.1 over 1.15 plus 1.1. And you will get the K2 is equals to 0.0067. For your K3, HF, X naught plus H over 2, Y naught plus K2 over 2. So your equals to H to 0.3 and your X naught is 0 plus 0.3 which is your X and over 2, then 1 plus 0.0067 which is your answer of number K2 over 2. So equals 0.3 F 0.15 which is 0 which is answer of your 0 plus 0.3 over 2 and your 1.0034 which is 1 plus 0.067 over 2 then equals 0.3 1.0034 minus 0.15 over 1.0034 plus 0.15 and you will get the T3 K3 equals 0.1478. For your K4, HF, X naught plus H, Y naught plus K3. So equals 0.3, 0 plus 0.3, 1 plus 0.1478 equals to 0.3, 1.1478 equals 0.15 over 1.1478 plus 0.15. And you will get K4 0.2306. Substitution of K1 plus 2K2 plus 3K3 plus K4, your equation. So Y times 0 X naught plus H is equals 1 plus 1 over 6 over 0.3 plus 2 times 0.0067 plus 2, 0.1478 plus 0.2306. And you will get the 0.3 equals 1.1599.
Modified Euler's predictor-corrector method. The predictor-corrector method is also known as modified Euler method. In this method, the tangent is drawn at a point and a slope is calculated for a given step size. Thus, this method works best with the linear functions, but for other cases, there remains function error. To solve this problem, the modified Euler method is introduced. In this method, instead of a point, the arithmetic average of the slope over an interval x sub t and x sub t plus 1 is used. Thus, in the predictor-corrector method, for each step, the predicted value of y sub t plus 1 is calculated first using Euler's method, and then the slopes at the points x sub t and y sub t and x sub t plus 1 and y sub t plus 1 is calculated, and the arithmetic average of these slopes are added to y sub t to calculate the corrected value of y sub t plus 1. So, here's the step. Step 1. First, the value is predicted for a step t plus 1. Y sub t plus 1 p is equals to y sub t plus h, where h is the step size for each increment. For the step 2, the predicted value is being corrected. While in the step 3, the incrementation is done x sub t plus 1 equals x sub t plus h, t is equals to t plus 1. For the step 4, check for the continuation. If x sub t is less than x sub n, then go to step 1. For the step 5, terminate the process. So, in this method, the average slope is used, so the error is reduced significantly. Also, we can repeat the process of correction for convergence. Thus, at every step, we are reducing the error by improving the value of y. For the next video, You are going to see the examples for the modified Euler's corrector method. Thank you.
Good day, everyone. So, this is predictor corrector method. Our sample problem is using Adam's predictor corrector method, find y of 0.4 correct to 3 decimal places given that y prime equals xy over 2, y of 0 equals 1, y of 0.1 equals 1.01, y of 0.2 equals 1.022, and y of 0.3 equals 1.023. So I have an step-by-step solution, guys, and solve this problem. So the step 1, less than all the equations, kanilang upat na equations, makuha na tong kanang answer, guys, which is y of, atong gipangita diri ang y of 0.4. So step 2, kaning step 1, guys, man yung formula sa in getting the h. Ang second formula kay y prime sub t. Ang third formula, y prime t plus 1 p. Ang p dira kay mano itong predictor. Nya atong 4 kay ikaupat na equation kay y sub t plus 1 c. C kay corrector. So ang step 2 na dito, guys, obvious man nga atong t equals 3 kay ngano, y sub 4 matong gipangita. So let t equals 3 kani t equals 3. Kunya kabauta na ang h nito equals x sub t minus x sub t minus 1. So ang mo came up to dira x sub 3 minus x sub 3 minus 1. So x sub 3 minus x sub 2 kay kanang 0.3, guys, ug 0.2 kay ari na gipabuhay. Diri 0.3 mga tong x sub 3 nya kaning 0.2 mga tong x sub 2. So atong answer dira kay 0.1. So ang step 3 kay y sub 3 equals 1.023. Given na sa, guys, kay ang x sub 3 na to man atong kagingon nyo ganina na x sub 3 unya ang y sub 3 nito ang equal niya 1.023. So pares na sila, guys, pares ordered pair na siya. Ang y sub 0 man atong x sub 0 unya ang y sub 0 na to kay 1. So x sub 1 na to kay 0.1 kunya atong y sub 1 equals 1.01. X sub 2 equals 0.2 kunya ang y sub 2 na to kay 1.022. Kumana to x sub 3 0.3, y sub 3 equals 1.023. So diri, guys, sa nadato sa diri sa step 3. So, y sub 0, ako gingan ninyo na x sub 0 times y sub 0, namday 0 times 1 over 2 equals 0. Sa diri, guys, kay tulo lang ka decimal places ang gamiton sa predictor pa nisa, sa predictor. So, y sub 1 equals 0.1 times 1.01 over 2 equals 0.051. Y sub 2 equals 0.2 1.022 over 2. Y prime sub 3 equals 0.3 times 1.023 over 2 equals 0.153. Using Adam's predictor formula, kani atong formula, standard formula sa Adam's predictor formula, katong ikatulo nga equation sa table na to sa step 1. So atong buhaton dira, i-plug in atong t, which is atong t dira kay equals 3. So ang t na to may mo siya 4, y sub 4 kay 3 plus 1 y sub 4. Kunya sa diri, y sub 3, y prime sub 3 copy lang y prime sub 3. Kunya y prime sub 3 minus 1 maning y prime sub 2. Kunya y prime sub 3 minus 2 kay y prime sub 1. Kunya y prime 3 minus 3 kani kay y prime 0. So atong button dira, i-plug in na nato mga designated na values silang variable. So y sub 4 P equals 1.023 plus ang h na to guys kay atong 0.1 na constant na ng 24 na 55 times y prime sub 3 which is 0.153 dere minus 59 y prime sub 2 which is 0.102 plus 37 times y prime sub 1 itong y prime sub 1 kay 0.051 mana kunya y prime sub 0 kay 0 so ato ni calculate guys i-fix na to itong calculator into 3 decimal places kaya itong ma-came up kay y sub 4 p which is predictor equals 1.041 so atong step 4 kay using Adams corrector na formula katong equation 4 sa atong table atong ikatulo kay predictor atong ikaupat kay ang corrector man na ang final guys so mga itong standard formula sa sa Adams corrector formula so atong t japon kay 3 however diri guys kay atong ini-calculate na to sa initial value problem or IBP kay mo gamit tag at least 4 decimal places para mas accurate siya. So diri atong gibuhat ano na guys, atong gibuhat pag una katong pag kuha nito sa initial IBP kay 3 decimal places naman to. Ato to i-calculate i-calculate to balik nya 4 decimal places atong gamiton. Sa diri y prime sub 4 p equals 0.4 anang 0.4 guys kay atong gipangita na diri y sub man to x sub 4 so atong gikuan dira kay 0.4 times katong answer na to y sub 4 p which is 1.041 na divide to ato ma-came up dira kay 0.2082 so sa diri na ta unknown since unknown maning tulo kani upat sorry upat so atong gibuhat dira nakuha na to diri kaning upat ato na i-plug in kanya i-fix na to atong calculator into 3 decimal places so atong answer dira kay y sub 4 c equals 1.041. So therefore, y sub 4c agrees with y sub 4p corrects to 3 decimal places. Hence, no further correction is required. So our final answer, kaya nakuha na to atong answer guys, which is 1.041. Y of 0.4 equals 1.041 is guys. Thank you and God bless.